Hello and welcome to part 2 of working with Linux drivers. The last slide deck was all about just sort of an intro to the kernel and getting our bearings on working around in what parts of the kernel we've got. Here we're going to talk about actually creating a driver, loading it, unloading it, and seeing how we can work with it. Now again, heads up, the coding in the kernel is different than you would be doing in coding in userland, in user space. We don't have printfs. We'll see what we've got instead today and realize that we're going to kind of plug into our code in a bit of a different way. We don't just have main, so pay attention to that. So what do we have? So we're going to look at getting that hello world of a Linux driver up and running and loading it and unloading it. We're going to see how to build it, and building it's actually pretty tricky too. You don't just call GCC and see what happens. And then finally getting some information on what we can do without printfs. So to start with, let's look at the Hello World, the driver edition. And how do we build this Linux driver? So first off, the thing we're going to do in it is we're going to try and print. And we can't print to the screen because the kernel doesn't really have a screen. It's got a sort of a default terminal that things can appear on. But really, kernel output ends up in dmessage. And the way we're going to get text into dmessage is through using print Ks instead of a printf. Print K is for the kernel. It is the kernel's printf. And its output goes to dmessage. So it's going to look like this, print K, and I'm going to put in the front here a kern info. This is basically saying what we call the log level, meaning how important is this message? Is this message like all right, we just detected this thing happened, whatever. Or is it like a critical, this driver had a memory protection fault and the system's going down or something? So the kernel level info, it tells us the level. Info is just sort of like, here's some basic information, whatever. And then whatever it is we want to print out. Hello world, for example, is this text. Now there's one thing here. Do you notice this line is strange for one reason? What's missing? There is no comma here. That's by design. Kern info is going to be a compile time constant string, like 5 or 12 or something, as a string. And it's then we have another compile time constant string behind it. The C compilers will take two back-to-back compile time constant strings like we have here, and that will combine them into one thing. And so this will actually end up being combined into one thing where it's printing out something special at the front. We'll see more on that in a minute. The other two things we need to know about our drivers is how does our driver run and when it loads and unloads. So when you load a driver, we're going to be dealing with runtime loadable drivers or modules. And when it loads, it's initially going to call some code. So the two things that really matter are hidden down here at the bottom. They're what really matters for startup. We've got this macro about module init and another one for module exit. Each of these are going to register a function that's going to be called. We can name this function anything we like, but we're going to probably call it init and probably call it exit just to keep it straight in our minds. But what really matters is these two macros. So module init, and then we pass in a function name, which is a function pointer, and say which function do we run when the module loads. And so we'll tell the kernel to load our module at some point with a command, and it will then, because of this macro, start executing this code. You can think of it a little bit like the constructor for our module. This specifies what that function will be, and then it runs this function at startup. Likewise, when we unload our module, it's going to come in here and it's going to run this. So module init and module exit are macros. They tell the kernel our functions to run at load and unload. Tells the kernel what functions to run at load and unload. Now, these are kind of complicated. I think the next slide actually is going to tell us a little bit about what is going on with this. The first thing we already know, incidentally, static makes it internal linkage. We'll see that in a sec. Okay, so what are these init and exit things we've got in our function declaration? Well, these are both GCC extensions to reduce memory use. So if the init function, whatever it is like our constructor, and the exit function, as registered down here, is like our destructor. These are going to kind of tag it as special cases. For example, the init, our constructor, is only needed when we start up a module. So if we're building this module into the Linux kernel, after the kernel has started, we're never going to run this function again. So it allows the kernel to free this memory after the kernel has booted. Likewise, if you've got an exit function, if it's built into the kernel, there's no way to unload it at runtime. And therefore, it's not needed when you're building it into the kernel. So it just doesn't build in this exit function if it's being built into the kernel. So these are a little bit about optimizations we got. So if we look at this whole thing, we've got the init and exit we now can understand as being like tagging this as the constructor, free it when we run the Linux kernel startup. The exit as in the destructor, don't need it if we're not able to unload it. Static, both of these statics make it internal linkage, and so that it doesn't matter what we name our functions, if some other driver or some other place in the kernel has a similarly named function, it's not going to conflict because we said it was static. So this is a key thing because you don't want your driver to somehow mess up the compilation of some other driver. And at the very bottom, we've got these macros. We saw the one about the module init, module exit. There's a couple other ones that provide us some information. So we say the module author, description, and the license. It turns out this license is kind of important. The kernel build system is actually looking for this. And if it's GPL, then it's sort of a first-class module and in there. And it handles different licensing things a bit differently. And it'll describe whether or not it's open source and that kind of thing. So we're just going to leave it as GPL for all the things that we're building. All right, so how am I going to build this? Let me show you a quick example on building here. All right, so I'm in my VM and I'm in my home directory. I followed the guide that will go through building a driver. And so I'm going to go into CMPT433, work, and then under here we create the brand new driver demo folder. This Linux folder and all these other files, incidentally, are also from following the guide, but that's part of the Linux build process. So I'm here. This is my folder that contains my driver. I have a make file and a C file. So let's run code here. Code on this folder. So let's look at the code. This is a full and complete Hello World Linux driver. You can fit it all on one page. What have I got? I'm including Linux modules. So this is from the headers in the kernel. And then at the very bottom with these, I'm going to read all of these almost bottom up. So we got the descriptions about what's going on. That looks fine. I've got my init and my exit. So here it is. Init's up to here. And just to show you, I'm going to say init something like, I don't know, yo-yo. And let's do a yo-yo exit, yo-yo as well. So I'm going to rename these functions here, yo-yo. Yeah, that's what I got. Yep. Just to show you that it can be named anything. It just has to match these about where we're linking things. This controls where it gets linked in the kernel. Each one of these, so the construction, initialization, returns a status code, 0 for success. When you're cleaning it up, there is no status code. You cannot tell it failed. You just simply must finish. And so we're not going to return anything. And in each case, I'm going to do a print K and something that's going to show up nicely in the DMESG. I'm going to save my file. And let's go build it. Before I show you the make file, I'm actually going to build it. So I'm going to run make here. Make loads the make file in my current folder, and then it goes through and it builds things. This output looks kind of nice. It tells us it's going to compile it, the drivers and so forth, and has made it. Now, if you remember from before, these were the two files I had in my folder. Oops, these are the two files I had in my folder to start with. Now let's see what I've got. I've now got a whole bunch more files. All of these are kernel build products that have gone through and sort of part of the build process. The one we really care about here is testdriver.ko. And the make file that we've got actually automatically copies it over to the NFS folder. So I think I've already got it here mounted. No, I don't. Mount, remote, and under drivers, I think it builds to. Yes, it deploys to drivers. This is the file that I'm interested in. This is the .ko file that automatically gets copied over to my drivers folder on a remote based on the make file I've got. So the last piece of the puzzle is let's look at that make file. So again, here are all the other files I don't really care about. I care about this make file. The make file is a bit complicated. It's basically going to exploit, leverage, maybe is a better word. It's going to leverage the kernel's build file. So we're going to specify here the kernel source. This is going to be under CMPT433 work Linux. And the guide will walk you through downloading, cloning the Linux kernel from GitHub, and then building it. And so we're basically configuring some of the build parameters for the kernel. And then it's going to go and run that build. What will then later happen is the kernel is actually going to come back to us. Oh, here's the rest of that. So it's going to come in and sort of run the build for the kernel. And then after the kernel has finished building, we're going to make this directory for the driver and copy our KO file to the right place. So this is kind of the added little bit of magic that puts things in the right spot. Now, the one weird thing is that this make file sort of executes twice. It comes in when we do the first make and does all of this and builds the kernel. On the second time, it's going to come back and kind of say, hey, we want to do this. And it's going to execute the build for testdriver.o, which is our file here. So if you're changing the name of your driver to something else, you're going to want to change this from test driver to something more interesting. All right, and so after that all is done and built, the build completes, it copies it over, so it copies this over here, copy all KO files to the public folder, and that gives us the file here. All right, so that's it to start with. Let's see what we can do. So how do we work with this KO file? Now that we've built it, and incidentally, getting it to build is not necessarily trivial. The guide will walk you through step by step, but there's quite a bit of computation time in terms of building the actual Linux kernel to start with, as well as I think 5 gigabytes of download. So how do you work with a KO file? Here are some of the commands we're going to need to know and get really comfortable with in order to work with these KO files, these drivers. First, we might want to list all currently loaded modules. lsmod. In Linux, there's like an ls USB to list USB devices. Well, lsmod lists modules. I can load a module with insmod, install a module, and then whatever name of my KO file is. So I got here name.ko. So whatever your file is named, we can install the module. Unload a module is rmmod, whatever name you want to remove. And we can view the modules. So mod info. This actually is quite useful. It's sort of like readelf. Readelf allows us to look at a binary that's compiled for user space and give us information about it. Mod info does the same sort of thing for the kernel. And we'll make good use of that because it turns out to be important. And one last one I want to show here, you don't necessarily need to use it, but it's a way to look at strings that are compiled into an executable. You can just call strings on some binary file, and it will tell you all of the ASCII strings that were found in it. This is really useful for spell check, in fact. You build your application, and you go through and you spell check just this to see if you've got any typos. But also it can help you maybe track down some of the information about what was the build configuration. Sometimes that's encoded into the executable file. So let's go ahead and try this out. I'm going to hop back over into my VM. And we're on the VM here. I'm in the folder with the test file. Let's get the information on that. So that's going to be, let me just zoom in a little, mod info on test driver, test./testdriver.ko. Give me the module info. So here it's going to show me all about that driver. Its file name, where it's found on disk, that's great. The license, again, it's pulling this. It's pulling all of these from those macros that we had at the end of our file. And then anything it depends on, we can say it depends on some other driver. This one does not. Driver name. And then there's this verm magic. Verm magic is actually very important. We'll talk more about it later, but it basically specifies the precise version of the kernel that we're willing to run on. So this is looking for kernel version 5.10.168. So if I do a uname -r, it tells me what I'm currently running. I'm using 5.10.168. Ha, perfect. And in fact, that's not just a fluke. When I go and compile the code, I specifically cloned or checked out the version of the code corresponding to what's running on my BeagleBone. If you're running a different version, you're going to want to check this and then set up the compilation for that. That's all available in the compilation guide. Okay, so this looks like it's going to be a match. Let's see what we can do with it. I'm going to start by running dmesg, dmesg, and see the last thing here we've got is the PRUs turned on at 46 seconds. So let's install my module. I'm going to insmod on my driver, which is testdriver.o. Now, KO, this isn't going to work. Why not? Well, you have to be the root user in order to install a new module, which is good because drivers run in privileged space. So I'm going to say sudo insmod, and that now ran. It looks like nothing happened, but my print K is going to come out to the dmesg, dmesg, and here we have it. We loaded an out-of-tree module. Now this taints the kernel. It sounds like we've got some sort of sin that is tainting all of our runtime. It's kind of like that. A tainted kernel means that you've loaded a driver that was compiled outside of the kernel source, meaning it's probably not from the mainline kernel, which probably means that the driver hasn't gone through the full QA that drivers would inside the main kernel. And so by marking this, it'll kind of come up in bug reports and so forth later on. While your system is running, having loaded a driver that is not built from the kernel tree, it registers as tainted, and so that's likely the problem if you encountered a bug or a crash later. But of course, we're not going to write any crashes, so that's fine. And then the big thing is here, we've got our output that we here have my test driver init. That's beautiful. All right, so let's check what's loaded. I'm going to do an ls mod. I got lots of things currently loaded here. All of these things for like sound and all this other stuff, CPU frequencies. And if I scroll up here, the very top one listed is the test driver. Very nice. So that's what we just loaded. Let's unload it now and see what happens. So I'm going to sudo rm mod on test driver .ko. Remove it, and I'm going to do an ls mod, and it won't be there now. It's gone. That's all gone. We don't have it in the list anymore. Let's check out what dmesg did. Dmesg, and there we have it. We removed our driver. Wasn't that amazing? I feel like that was amazing, right? We got the kernel to put something in dmesg through a driver that we loaded. Now our driver didn't do much, clearly yet, but we will get into that in a little bit more later on. Okay, and the last thing I want to show is strings. I'm going to use strings on this. Strings, hopefully I've got it installed. Test message. There we go. And these are all of the strings that are existing inside of this binary. So remember before we said the print K and how it was going to have that thing at the front, the mod info? Well, there it is. There's that 6 that tells us the info level. And here, same one, another string. It's got a 6 there. That's good. Other strings that we've got here, license, description, author, depends, name. We got the version magic that's listed here, and a bunch of other stuff. These are the things it needs to actually link and compile. We're not going to worry about all this, but it's nice to know that it's there, it's accessible, and we can start to gain a little bit of visibility inside of our module. So the big thing you want to do if you want to get information is you want to run mod info on your file. This is the primary way to get information. And the thing, again, that we care most about is this version magic. All right. So let's carry on with print K. So here's another print K just to kind of walk us through. We can see here that we've got kind of, if you ignore the current info at the front, it kind of looks like a standard printf. Hello, %d, %s, so for d for a decimal, s for a string, and so forth. The big thing to remember is there's no comma here. What's happening is that this current info, which is going to be a string like quote 5 quote, is going to be right before this other one with only white space between, and the compiler will concatenate together hard-coded. Oh, let me actually make it so everybody can see this. There we go. The compiler is going to concatenate together strings that are adjacent to each other with only white space in the middle. So that comes together as one thing. These log levels are going to be found in the kernel include Linux kern levels.h. Let's go find that. Let's have a look at that now. Let me go back to my code here, and I'm going to jump into this corner, and I'm going to go back on my host. Let's zoom in a little here. I'm going to get down one level, and here I've got the Linux folder, which I've actually cloned as per the Linux guide that I've got online, the kernel guide, Linux. And then in here, we said it's going to be under the include folder. Include. Here are the include folders. We're looking for Linux, under Linux. And then here are a bunch of them. I'm going to ls kern star. We want kern levels.h. So let's code kern level, or kern underscore, pardon me, levels.h, and look at that file. And so here are all the ones we've got available. We're currently doing at info, so informational. You can go to debug at 7, which is even less critical. It's just a debug message. But as you work your way up, here's normal but significant conditions, so something that's kind of interesting to note. A warning up at warning, error conditions, critical, alert, action must be taken, and emergency, system is unstable. So we can pick which one of these our message best relates to. So that's all related to when we're doing the print or the print case. So we're usually going to use kern underscore info, which is defined to be 6, but other ones are still viable too if it makes sense in your particular application. So by using a print k, we put a log level at the front. We then have access to the regular printf stuff, somewhat. There's a few things they've added to it. Note that if you have important messages, you can actually set a threshold in Linux and tell it to print messages that are more important at that importance or higher than that threshold. This is useful for debugging sometimes if you want everything to pop to the screen. We'll probably just stick with using dmessage whenever we want to see the output, but it's possible you can go through these proc sys kernel print k file, and you can then find out what the current log level is. And that'll just define what gets printed to the default console. Okay, so a quick aside here, through U-boot you can actually also specify Linux's log level. So one of the things we've got is the boot args in the U-boot, which is the command line arguments that are passed to the kernel when it runs. And so we could append to that this log level equals 3, and that will change the level of information that's printed out to the screen. So sometimes some configurations you'll run it and it'll print a lot of stuff at startup. Other times it won't print much at all. That's all based on this log level, settable via U-boot. And I think I'm going to skip over demoing the log level here just to check the scene. Okay, so that was it for this. A nice short video on looking at what goes into a driver, how to load it after we've compiled it, and the ways that we can interact with it. So we saw the print K and printing messages to our screen, or to our dmessage. We talked about the mod info and mod exit that we have used to specify what code is going to run as basically our sort of constructor and our sort of destructor. And we talked about working with that KO file and all the different commands. All right. Thank you very much for watching. Happy coding.